Okay, everybody, welcome. Thank you very much for joining us today for our second webinar event in the CSE3 Summer Sustainability Series. The Center proudly supports and sponsors this event today. We're very glad that you could join us. Hopefully the weather keeps us all together. I know the storm is coming over for many of us in Eastern North Carolina right now. And stay safe, everyone. Just to get started, to let you know the mission of the Center for Sustainable Energy and Environmental Engineering, or CSE3 for short. Our mission is to provide scholarly and applied research and consultancy for sustainable energy and development, and natural resource conservation. We enhance public awareness of renewable energy technology and natural resources by focusing on research and workforce training. And we seek to establish partnerships with businesses and organizations, industries to foster the efforts that benefit North Carolina communities. Additionally, the Center also receives grant funding through the EPA for multiple research projects, including all types of environmental and energy management, excuse me, and event pollution prevention. I'm so sorry. We provide energy and lean assessments to different North Carolina manufacturers, regional workshops, on-site face-to-face training, one-day training classes to promote environmental management and energy management. Some of the programs through the pollution prevention program that we are working with right now is pollution prevention, making it pay for North Carolina industries, which will be our next event on July 29th. We also work with food and beverage industries, other, sorry, back and forth here, automotive, chemical, and fabrication manufacturing industries as well. We also receive sponsorships, corporate sponsorships and donations to the public to continue student research engagement, to be able to host these type of webinar events and to host them free, and offer many scholarships to students associated through the center. Just another little note, if you're interested in our next event or any of the following events, registration is still open. Please share it with anyone and everyone. We want to reach as many people as possible. Just a little bit of housekeeping before we get started with our speakers. We're just asking everybody to kind of hold off on your questions until after the presentations. We'll open a Q&A forum for discussion. If you don't wish to speak or be on camera, that's totally fine. You can send me your questions through the event chat here, and I will ask them for you, or get your question to the right person. If you need to leave early, you can also drop any questions, or everyone should have my email at this point. You can email me any questions. I will make sure that your question gets to the right person. When we do get to the forum, just feel free to unmute yourself and ask questions, or raise your hand, or whichever way you want to go with that. We've allotted 2.5 hours today for this webinar. We rely on your participation. We may not use that whole time, but we may. And if we do end up pushing the 4 o'clock time frame, if you want to stay on, I'm sure our speakers will be happy to answer any questions afterwards. Also another side note, we are recording today's event, just to be aware. If you don't want your image to be shared, please leave yourself off the camera. Additionally, you should have all of today's presentations in the shared file in OneDrive that I sent everyone a link to today. If you don't have it, you will have it at the end of the meeting today. I know there are a couple people that registered at the last moment. If you're having any trouble, just let me know. And then the recording file will also be uploaded by tomorrow. So with that, I just want to go ahead and introduce today's speakers. We're going to start off today with Mike Stowe from Advanced Energy in Raleigh. He's a senior energy engineer specializing in industrial process energy efficiency and strategic energy management, excuse me. He has over 30 years of involvement in manufacturing plants and energy efficiency work. I'm sorry, y'all. Mike has extensive experience with many industrial processes and all types of plant facility support systems. He works with utilities, industrial equipment vendors, manufacturing plant teams to find best technical and most energy efficient solutions for industrial processes. He's earned numerous credentials and certifications and is nationally recognized subject matter expert in the ISO 5001 and SEM. He serves on several industrial process trade associations and ISO 5001 related boards and committees. Thank you, Mike, for being here with us today. Next,
thank you.
Yeah, absolutely. After we hear from Mike, we will hear from Kevin McKeel from Piedmont Service Group. And Kevin has over 30 years of experience in maintenance and commercial and industrial machinery and facilities. He has completed the facilities engineering management certification, and the energy management certificate at NC State, and has passed the professional energy manager exam through the Energy Institute. He's a certified plant manager, certified plant maintenance manager through the Association for Facilities Engineering, and he holds a North Carolina electrical contractor's license and refrigeration contractor's license as well. Thank you very much, Kevin, for being here with us today.
Thanks.
And then, last but not least, we will hear from a former pirate himself, pirate alum, Sam. Sam Myers is a building scientist for Retrotech, where he teaches building science concepts at conferences and event training, much like today. Conducts field studies and assists Retrotech with new product designs. After the pandemic, most of the industry's conferences and trade shows had been moved to online platform. So to keep providing the industry with quality educational material, Sam built a virtual training lab in his home, which he is sitting in right now, where he has taught and trained contractors and consultants all over the world. He's also spent several years as a building scientist with Advanced Energy, also where he has known Mike, one of the most respected efficiency consultancies in North America. He managed field operations for building performance programs and served housing developers that included Habitat for Humanity. He has a master's of science from East Carolina and is also a certified HERS rater and is a licensed real estate broker. And Sam also lives in Wilmington, where he's also getting pounded by the storm as well. So thank you very much, Sam, for joining us.
Absolutely. Thanks for having me.
Absolutely. All right. So at this time, I'm going to go ahead and turn the platform over to Mike.
Thank you, Kara, for that introduction to the group and what you all are about, and the speakers. We thank you very much for having us today. We look forward to it. I know if Sam and Kevin are like me, they love an opportunity to talk about energy, so we appreciate it very much. So I'm going to share my screen. You all should be seeing a title page with electric power lines and so forth, sunset. First part, we have three parts, three speakers today, but the first thing we're going to talk about is a kind of an overview of industrial energy efficiency, some of the tools, some of the assessment methods. Sam and Kevin are going to add to this as well. So we'll go ahead and get started. So first is kind of an outline of what we're going to talk about today, kind of the big picture of energy, and why do we worry about energy so much, especially in industrial areas? Energy efficiency and energy intensity, two different aspects of energy. Where to look for energy efficiency? Basically, if you look at a manufacturing plant, there's really two things going on. There's all the processes that are making the stuff. If they're making bricks, or if they're making peanut butter, or if they're making furniture, all those processes that make the product, and then all the facility stuff that supports it. Like Kevin will talk in detail about chillers and other things, boilers, air compressors, lighting, all those other things. And then we'll talk about some tools. And we really appreciate ECU having us today. And this picture over here on the right-hand side, that's just kind of a graph of kilowatt hour demand over 2 weeks at a manufacturing plant. And if you can really get a good feel for this and how you operate, you really can reduce some of these peaks and reduce some of this overall energy consumption. And that's what this is all about today. So energy, the big picture, there's a 25 question exam after the session today on this picture. So memorize this really quick so you'll know about it later on. I'm just kidding. But this is a spaghetti chart for sure. But this really, all the left-hand side, all these things over here are energy sources: solar, nuclear, hydro, and so forth. And then you got what I call all the dead dinosaurs, all the fossil fuels, natural gas, coal, biomass, which is like wood or sawdust or burning something like that, and petroleum. And basically what this does is it takes all these energy sources and then splits them across to where they're consumed. And the DOE energy group does this every 2 or 3 years. The latest one was in 2018. I think there'll probably be another one out in 2021. But this basically, the United States consumed 101 quadrillion BTUs of energy in 2018. Now, a quadrillion is a one with 15 zeros. So you got million, billion, trillion, quadrillion. These quadrillions are even more money than the federal government spends. So it's a pretty big number. But you can see over here, industrial is around 26 quadrillion BTUs of energy consumed in 2018, mostly by far from natural gas and petroleum. A little bit of coal, a little bit of biomass, and a little bit of electricity. And sometimes that surprises people how small the electrical portion is for industrial, but it's a lot of natural gas processes in industrial plants. And also you can see electrical generation is made up a lot of natural gas and a lot of coal. It's still, most of the coal consumed in this country is for making electricity. So that's just kind of a big picture. And if you break that down, industrial is about 35% of all that. Transportation, which includes airplanes, boats, cars, tractor trailer trucks, is about 37%. And then commercial and residential add up to about a third. So it's about a third, and a third, roughly. And then if you break down all the industrial energy consumption by type, natural gas and petroleum are the huge energy sources that are consumed by manufacturing, with electricity, some biomass, and a very small amount of coal is still used. So that's kind of a big picture of what energies are used in industrial and how much, and that's why there's so much energy consumed by manufacturing processes. There's lots of opportunities to become more energy efficient. I love this little graph. You can apply this to anything. This little graph could be a motor, an air compressor, an entire building, the entire ECU campus. You can look at it in any number of ways, but basically you bring energy into a system, a process, a building, a site, and you pay for that energy. You have paid your power bill, you have paid for that natural gas and that electricity. Now it's in here. Now what are you going to do with it? Hopefully, most of that energy is going to add value. You're going to heat up a piece of steel, you're going to bake a cookie, you're going to cure a brick, you're going to cure a coating, you're going to melt some metal, you're going to do some process that adds value, and hopefully these losses are minimal. So you can look at this from one natural gas oven, you can look at this to an entire site or an entire country. But what we want to do in manufacturing is we want to make more stuff, bricks, cookies, whatever we're making, with less energy. And to do that, we want to make this loss, this peel off of this energy we bring in, this little curve that peels off as losses, as small as possible. So our energy going into our product is as close to 100% of what we bring in as possible. It's not physically or thermodynamically possible to get 100% efficiency. You're always going to have losses. But believe me, there's lots of losses here that are absolutely easy and inexpensive to find and get rid of and reduce these losses. Energy intensity, on the other hand, is like the amount of energy from all sources that you require to make one logical unit of product, and is the energy per unit of product. So it's an intensity factor that gives you an idea of how much energy it takes to make a brick. And here's some examples from industry. For a foundry that's melting steel, maybe they look at total MMBTU per ton melted. Or if it's a textile mill, maybe they look at energy MMBTU per linear yard of cloth that they produce. Or maybe if you're making individual widgets like a gear plant, maybe you look at how much energy per part or per gear. Or per car or per whatever individual unit you're making. And that energy intensity can give you an idea of how much energy you're consuming per unit of product. And energy intensity and energy efficiency are related in that you want to increase your energy efficiency, reduce those losses, and thereby for a given amount of product, if you use less energy, you're going to reduce your energy intensity. So your energy per gear, your energy per ton will go down. So you want to increase energy efficiency to reduce your energy intensity. And those are both great goals for a manufacturing plant to work on. So how are we going to do this? Where can we find energy efficiency? Where can we find it? How can we save energy? Where do we look for it in a manufacturing plant? We're just going to hit some of the high topics here. Basically, as I mentioned earlier, there's two key areas. The process, if you're in a manufacturing plant, you are making parts. You're making a component, a gear, something that goes somewhere, or you're building a complete product. And then all those processes need support equipment, chillers, which Kevin's going to talk about in some more detail, HVAC and chiller equipment, boilers, motors. Most manufacturing plants, easily 50 to 60% of their electricity is consumed by motors, turning something, turning a pump, turning a fan, turning a compressor on a chiller. Turning a blower motor on an aeration basin in a wastewater treatment plant. Motors are everywhere in manufacturing plants, and big ones, 100, 200, 300, 400 horsepower. They consume a lot of electricity. So really focusing on these two areas, you can really figure out where to get some energy efficiency. So looking at processes, every manufacturing plant you go to is going to be slightly different. One of the first things we want to look at when we go to a manufacturing plant is what's on the receiving dock. What are they bringing in? Are they bringing in potatoes, corn, and green beans and making vegetable soup? Are they bringing in peanuts and making peanut butter? Are they bringing in raw steel plate and making a chiller like Carrier, for example? But anyway, whatever they're doing, they're transforming some raw materials into a final product, and that requires energy. They're changing the form, the appearance, the nature. Maybe they bring in flour and sugar and butter and chocolate chips and make chocolate chip cookies, but whatever they're doing, they're transforming. And here's a very simple example. You can take a lump of clay and you can make a painted vase. That's a very simple example of transformation. You take this raw material, you apply some labor and some energy, maybe an electric kiln, you paint it and cure it, and now you have a finished product. That's transformation. That's a very simple example. Now let's think about a more complicated example. This is a piece of round steel bar, maybe 4-inch or 3-inch diameter, and we're going to make, this is a mouthful, we're going to make a fixed outer race front wheel drive half shaft bearing housing. This is where the wheel goes. So when you're steering your car driving down the road, this piece right here allows you to turn your wheels and let the engine drive your car. It's a front wheel drive device. And just about every car with front wheel drive has one of these of some type. So this is much more complicated. So how on earth are we going to figure out where the energy goes to make this? Well, one process we use is a process block diagram. You map out each step of the process. You determine where the energy comes into the process, and you determine where your wastes are, and then you can see where you might have some energy efficient opportunities. So this is an example of a heating process with induction, where you have a coil and you heat a piece of metal. So that's consuming energy. So thinking about this process, here's a manufacturing cell that makes these, and you might have, 20 different blocks of energy, of manufacturing processes to get this made. Starting from this raw material, you go through all these steps, and now you have this final part. Well, detailing this out with energy, you can really figure out where your energy goes. And I've just got a few examples. So maybe you have an induction hardening process. And so you have an electrical power supply and electricity feeding that. You probably have an oven where you temper these metal parts in an oven. So you have natural gas combustion, you have flue gas, you have electricity running the fans to circulate the heat in the oven. You kind of get the idea. And if you spread this out across an entire plant or a process, you can figure out you have a washer to wash these parts after they've been manufactured and before you paint them. So you may have a boiler with steam to heat the washer. You may have some circulation pumps or so forth. So you see, in this case, you got natural gas, you have steam, you have electricity, and you map that out across the entire plant, and you really can get a good idea of where the energy is consumed, but also losses. If you have a boiler or making steam, that hot flue gas is going up the stack. That's an energy loss, and maybe there's a way to recover that. Again, you want to minimize losses. So thinking about, flue gas up a stack or wasted compressed air leaks or things like that, you definitely want to reduce this part of the loss. So the maximum amount of energy that you pay for gets value added into your processes. Okay, let's look at the facilities a little bit. We'll touch on a couple topics here in facilities. Facility systems support the process, and these are common in just about every manufacturing plant I've ever been in. Everybody has lighting. You have to have lighting. Most every plant has compressed air. Some have more than others, depending on the process. Every manufacturing plant has motors, and lots of them. Some have variable frequency drives, which are certainly an opportunity. And a lot of plants have some type of combustion, either for a boiler or for some type of oven or furnace to where they're heating. And there's some waste heat recovery opportunities. And then, of course, chillers and HVAC, which Kevin will get into more detail a little bit later today. So lighting, the word for lighting today is LEDs. LEDs are the latest and greatest. They've come way down in price. There's lots of different options, from these little things down here to a full 4-foot LED strip replacement. You can drop right in a 4-foot fluorescent fixture. So there's all types of LEDs. There's lots of utilities like Duke Energy in North Carolina that provides incentives for replacing lightings, and lots of vendors are set up to do this. They'll file the incentive, they'll help you. So upgrading lighting is a very common energy efficiency project that you see very often and that we recommend all the time to manufacturing plants, warehouses, commercial buildings, and even at your home. So lighting, the LED is the way to go. They're way more efficient than like a 400-watt metal halide overhead light in a factory can be replaced with something on the order of a couple 100 watts or even less, a third or a fourth of the wattage to get the equal lighting. Compressed air. We could do a whole week's study on compressed air. Compressed air is the most efficient energy source or utility in your plant, typically from the electricity to the compressor motor until you actually get the compressed air out to where it's doing something in the plant, is about a 10% efficiency. It's absolutely terrible, and it's expensive. Just one data point, if you have a 150 horsepower air compressor running fully loaded and you pay in about 5 cents per kilowatt hour, it'll cost you about $50,000 a year for the electricity just to run that 150 horsepower compressor. And if you have a 10 or 20% leak rate of your air, you can see that you're compressing 20% of this. So $10,000 a year is going to just make leaks. And that's terrible. And that's in every single plant. And typically there's an attitude among people in plants that, open this valve, there's compressed air. It must be free. It's just there. It's everywhere in the plant, anywhere I want it. But it is not free. It's very expensive. But this attitude that it may be free or it's just available everywhere makes sometimes people think of unusual ways to use compressed air, which can be very harmful to your efficiency, like personal cooling. I've seen compressed air used for personal cooling. It's the most inefficient way to cool yourself off. It's very expensive. You could buy 1,000 fans and run them all year for what it costs to use compressed air for cooling yourself off. Compressed air leaks. Typically, we see 25 to 30% of a system capacity is leaking air. It's everywhere. Here's an example of something. This picture, all these little pipes are off this one header, and they're just blowing compressed air out of all these little tubes, probably to dry something off or to blow dust off something. But there's 1,000 different ways to do this without using compressed air that are much more efficient. So you want to educate people, you want to do plant surveys, you want to remove improper uses, have a strong leak repair program, having the right size compressors running and operated correctly. You always want to base load a compressor. Compressors love to run at 100%. They're most efficient when they're fully loaded. And then if you have a compressor with a VFD, it's designed to run at various loads and be efficient across a range of loads with the various variable frequency drive, which it can slow down and speed up as your load of compressed air in your plant goes up and down. A trim compressor with a VFD can float that, and you base load just a regular compressor without a VFD, and that's a very efficient way to do that. Nozzles, they make very efficient air nozzles that use the minimum amount of air for blowing air. Every plant I see, you see people blowing down dust or cleaning or using air hoses for all types of stuff. Minimize the system pressure. Don't operate the plant at 150 psi if you can run it at 120 psi. There's a rule of thumb that if you can reduce your air pressure by 2 pounds per square inch, you can save 1% of the compressor energy. So if you're running at 120 and only need 100 and can reduce your air pressure to 100 psi, that's 20 psi. That's 10% of the cost of the energy to run those compressors. Controls, updating how the compressors are started and stopped, looking at alternatives to compressed air. Use a 20 psi blower, use some kind of mechanical actuator. Evaluate the waste heat recovery from compressors. It's not a lot. It's not like combustion from natural gas, but there is some things you can do with the waste heat from a compressor. Bag houses are big filter houses that filter out big processes like foundries or somebody that makes a lot of dust, textiles. They use a lot of compressed air. And if there's a bag house in a plant that you're looking at, you need to think about evaluating your bag house system. It's the most important expensive support system. That means the paybacks can be very good. You can get excellent capital paybacks on capital projects, but repairing leaks is almost free and almost has an immediate payback, fixing leaks. One thing to think about, air is odorless and colorless. So if it's leaking, you can hear it. If it's a big leak, you'll hear it. But if you have a water leak or an oil leak, that's going to go out on the floor and make a big puddle, and everybody's going to see it and mop it up. But you would never leave an oil leak or a water leak unattended for months and months because it's in the middle of the floor and everybody sees it. Air leaks kind of get forgotten because they don't see them and they don't smell, and there's not a mess, but they are very, very expensive. Motors and variable frequency drives. This is a great area to focus on. Electric motors typically account for 50 to 70% of all the electricity consumed in a plant. In air compressors, chillers, HVAC, fans, hydraulics, material handling, you name it, there's motors everywhere. And we've implemented motor management programs and saved roughly between 6 and 8% of the total energy consumed by motors by looking at things like having a policy to buy, the best motor, the most efficient motor and things like that. VFDs are very, very effective if there's a variable load and you can reduce the speed of the operation, say chilled water or a fan, you can slow those down parts of the day. The ratio of energy to the speed is to the cubed power. And an example of that is if you reduce the speed of a fan, for example, by half, that's 1/2, or half cubed is 1/8, and you actually only need 13% of the total power to get to run the motor at 50% speed. That's huge savings. If you have fans that are running at full speed all day long, but you don't need that much airflow all day long, there's a good possibility you could put a variable frequency drive on that fan and a thermostat feedback or some kind of air pressure or temperature feedback, and slow that fan down during parts of the day and save lots and lots of energy. Always use NEMA premium efficient motors. If you look at the 20-year life of a motor, 96% of the cost of that 20-year lifetime of that motor is the energy, the electricity it consumes. So if you can convince purchasing to spend $500 extra to buy that 96% motor, efficient motor, instead of that 94% efficient motor, that's cheaper, but over that year, that 2% difference in the efficiency of that motor over this out here, you're going to pay that back 100 times over. So use NEMA premium efficient motors always. Motor management, we talked about that. It's a great idea for maintenance or engineers, purchasing, to understand a motor management program and have a database for your motors and look for nameplate data, even maybe take pictures. We set these up for people all the time. It's a great way to manage your motors. Talk about a little bit about combustion. Combustion, natural gas, methane plus oxygen gives you carbon dioxide and water all day long, every day. You reduce how much natural gas you're burning, you will reduce your carbon footprint, period. Less methane, less carbon up your stack. You want to reduce your carbon footprint, stop burning so much natural gas. And there's alternatives and efficiency ways to do that. Balance your air and fuel. This is a very simple graph. There's a very sweet spot at about 2% excess air that gives you the most efficient combustion. If you get too low in oxygen, you're going to form lots of carbon monoxide and soot. If you get too high, you're going to have NOx or nitrous oxide and things like that. So you really want to get your burners for combustion processes tuned very well. You want slightly excess air. You never want excess fuel. And you'll be very efficient in your operations, but you got to manage that and maintain your burners to meet this. When you burn something, it gets hot. When you get hot, you're going to have losses. The building we're in is 80 degrees. This combustion's at 1800 degrees. So you think about all this natural gas comes in, you combust it, most of it goes right up the stack, or a good portion of it. You're going to heat up your furnace. You're going to lose some heat there. You're going to lose some heat here, and maybe a third of the natural gas you combusted actually goes and does something useful to your part or your cookie or your brick or your coating or whatever you may be curing or heating or cooking. Some possible uses for waste heat. Waste heat going up the stack. Again, if you look back here, this heat going up the stack, there's got to be something we can do with that. You can preheat combustion air. You can make steam, maybe. You could maybe generate some electricity with all this waste heat. There's lots of things here that you can see. Here's just an example. You got a combustion here, some type of furnace or boiler. This heat goes right up the stack. Well, if you bring your air, you have to blow air in here to make this combustion happen. So if you have a recuperator where the stack heats this incoming air, about every 40 degrees you can pull out of this exhaust gas, you can increase the efficiency by 1% of the combustion. So that's a very easy, again, retrofitting this might be expensive. If you had a new project, you would definitely want to buy something with preheated combustion air, just something to think about. All this waste heat, though, can you preheat water? Do you need lots of hot water? Maybe you put a water to flue gas heat exchanger here or something like that. One of the other benefits of all these projects, if you do these energy efficiency projects, are non-energy benefits. Maybe you do an energy project and find out that, wow, this improved our quality or our productivity or reduced our scrap, or the workers are more comfortable, or we have more floor space, improved safety, reduced emissions. So especially if you think about carbon, a lot of people are concerned about their carbon footprint. If you can reduce combustion consumption of natural gas or coal or fuel oil in your plant, you're going to reduce your carbon directly. Electricity will do the same thing, although it's based on how the electricity is generated, but natural gas reduction is direct. So the big picture is you want to continually improve your approach to energy efficiency. You want to get on the plant floor, understand the processes, see what they're making. Is it brick? Is it clay and bricks? Is it peanut butter, peanuts and peanut butter? What's being transformed? What are the processes? Analyze the steps of that process. Recommend energy solutions, follow up, and then a year later do it again. And you just continually squeeze all the energy you can out of your plant. Some of the programs, tools, and resources that are available. Electrical utility account executives are great. We work very closely with the co-ops in North Carolina, Dominion Energy, Duke Energy, Georgia Power, TVA. We work with electrical utilities all the time, and they have lots of programs. Sometimes they can help with capital projects. Sometimes they can help with infrastructure. If you have, aging transformers, keeping your business going, incentives for electrical efficiency programs, your electrical utility account executive is a great resource. There's also lots of government programs, DOE, EPA, they have lots of programs. There's a Better Plants program. There's 50001 Ready, which is an energy management system. ISO 50001 is an international standard for energy management that a lot of people use. That program. Superior Energy Performance is a DOE energy management program. EPA Energy Star, EPA Water Sense, lots of other energy programs. But check all these out, and I do have this list of links here, which you will get with the PowerPoint. You can check these out, EPA, Better Plants, and so forth. So there's lots of opportunities for energy programs and resources. There's lots of things to look at. There's a resource of personnel or certified personnel at this link right here, the Institute for Energy Management Professionals. You can go on this link and look up, ISO 50001 or different energy things that you might be interested in, and it'll give you a list of people that have these credentials and that could help you with any energy programs that you might be interested in. But just remember, it's an ongoing, it's not a project. You don't say, well, next July we'll be finished with our energy project. It's a process where you plan your energy, you execute your plan, you check to see how that went, and then you act to fix it and make it better. And it's an ongoing improvement process of continuing to find energy to save. And that's all I have right now. So we'll move on, and then we'll have some questions later on. But energy efficiency there's a world of things to find out there, and it's just a matter of tracking them down and fixing them. So I'm going to stop presenting and pass it on to Kevin. I think you're up next.
Thank you very much, Mike. I appreciate that a lot. That was a lot of interesting information. It made me think of my dad telling me when we were younger to close the door. We're not heating or cooling the outside.
Yeah, it's funny how many manufacturing plants try, and Kevin knows that too, how many manufacturing plants you have to fight to get the doors closed and all that natural gas going up the chimney and windows open and cooling the whole neighborhood.
Right.
Or heating the whole neighborhood.
Right. Well, thank you so much for your presentation. Again, all that information is available, has been shared through the webinar space itself and through the OneDrive. If you have any questions specifically for Mike, we can ask later, or his information is at the end of that presentation. So we'll go ahead and move on to Kevin now. Kevin, I'll just have you take over.
All right, thanks, Mike. Mine will be probably a little bit simpler program. Am I sharing?
Mm, not
How
yet.
about now? Okay.
Yeah, there it is.
There it is.
All right. Mine's a little bit simpler program. Mike has some very good ideas. But what drives energy conservation? Typically, behind raw materials, the top three costs to produce products are labor, transportation, and then utilities. We often can blame our high energy cost on the power company, the oil prices, the government. We can pick any excuse, and there are plenty of others. We can even reason that other companies face the same high costs that we do. To me, it's real simple. If you can afford to pay the bill, then it doesn't matter. You can sit back and do nothing at all. But we're all in a highly competitive market, so we have to look at how can we cut our energy spend. To define HVAC effectiveness, the first step requires us to clearly define acceptable operating conditions on the key measures of the production process. So what temperature and humidity is required? Are we cooling for process or comfort cooling? Most people in manufacturing plants really think that we're cooling plants down for comfort cooling, and in essence, we're doing it for the process. Most people say that as long as you maintain the temperature between 72 and 76 degrees, then it's effective. But is the humidity correct? Do we talk in terms of dew point? Most of the time it's gauged by our customers, our operators, our associates' complaints. So temperature and humidity are measurable parameters that define an effective HVAC system. Only after the factors of temp and humidity have been satisfied should the issue of energy savings really be considered. So are we measuring HVAC effectiveness or our customers' tolerance for heat? You got to have a clearly defined goals. I've seen a number of places that you walk in and the temperature is fine. They're actually cooled down below the 70s, but the humidity is way out of control because they're overcooling the space. They've reduced some load. They've changed something. June, July, and August, there's really not a lot you can do but try to keep people cooled off. People complain people complain. So in order to make complaints go away, we tend to turn our backs on energy management. But the remaining 9 months is where we should put most of our focus. So how do we learn our HVAC systems? We start out with surveying and cataloging the equipment, getting brands, models, serial numbers, collecting any and all data that can be used. We review all our drawings, design parameters, and OEM manuals of the systems to understand what the systems were designed to do. Review startup log sheets and any commissioning reports. If the systems were installed properly, the systems are or were the most efficient at the time of the commission startup. So reviewing those sheets will tell us how they compare. We understand the system components and how they work. Monitor and trend the HVAC system to establish benchmarking for production processes. In graph form, how can we show that the temperature affects the process? Many times I've taken production data and put it beside temperature and humidity to determine when the production is affected the most. We compile weather data and study the effect on the plant HVAC systems. I've been running a spreadsheet that I've kept for almost 20 years, grabbing the monthly average on weather underground and then taking that and plotting it against utility bills to determine when something looks out of whack. Review the current CapEx plan if you have one. CapEx being a capital expenditure plan. ASHRAE has published a chart that lists estimated life expectancies for various HVAC equipment. So where are you at in the life cycle of your equipment? Attached to this presentation should be some an ASHRAE sheet given the life expectancy of most equipment. Rooftop ACs are generally last for 15 years. Heat pumps, 15 years. Chillers and cooling towers have a 20-year life. Electronic controls have a 15-year life. And then now we're at a very unique time in the life of equipment because we are at the end of the life cycle for R22 refrigerant. If the last year that equipment was made using R22 was 2010, and now we're finding it very difficult to get replacement parts. So that brings on a different talk as to when do you replace your equipment. So ASHRAE gives us some guidelines for audits. A preliminary audit gives us rough estimates of kW per square foot. How does that compare to other facilities or other industries? A level 1 audit, we go in and it take that basic audit and expand on it. It's designed to give businesses a starting point for making changes or further in-depth auditing. We use it to interview key people and review facility bills and prepare for a level 2. A level 2 comes along and it's for businesses wishing to improve energy efficiency or hone in on how the whole building is functioning. It identifies projects that will provide the greatest energy reduction at the best return on investment. Then you get a level 3 audit, and it takes the findings and recommendations of a level 2 and offers more in-depth engineering analysis. Detailed gathering of data in the field is conducted and analyzed for more intensely areas of improvement and potential cost savings. Gathering data and keeping accurate track of system performance helps troubleshoot and solve problems before they become a major headache. So how important is benchmarking? Benchmarking measures key operating factors. You must assess the current situation by using monitoring and verify that processes are operating at acceptable limits. Benchmarking provides us with useful information for trend analysis and helps us to understand cause and effect and the relationship between processes. How can you improve the process if you don't know what the process is doing? I've often heard said it feels hot. What does that really mean? We must have some method to measure the performance of our system to using benchmarking areas where savings opportunities have been found. I like the statement, if you're not measuring, then you're not managing. So a little deeper, you can take those benchmarks and look at HVAC systems, motors, frequency drives, substations, compressed air, lighting, and look for opportunities to save. Benchmarking energy can then be charted against your the cost to produce your product or financials or output using units of production. What is your unit of production? With that, once you know that, you can chart the cost in kW per pound or dozen or unit, kW demand and distribution, load factor and utilization, which is how well we're using power, develop a cost per day, kWh per day, etc. Benchmarking will allow you to predict the outcome. On a certain day, this is how the building will react. If we do this repair, this is who will be affected. This is what a day will cost us to operate our facility. Once you're gathering that information, you can put true costs to repairs, to operations, to making improvements. It's important to take time to review which benchmarking measures have the greatest payback. And again, if you're not measuring, then you're not managing. You got to keep a score of how we're playing. Some simple temperature checks can be made at supply registers with an IR temp gun. What should the temp be? In AC mode, the supply temperature should be the room temperature minus 12 to 18 degrees. In heat mode, the supply temperature should be the room temperature plus 35 to 40 degrees. This can be a simple exercise taken one time a day, entered in an Excel spreadsheet, and used to compare against other factors. Other tools that can be used to measure your system's performance are a voltmeter, ammeter, electronic psychrometer to measure humidity and dew point, flashlight, IR camera, hobo data loggers, which can then be downloaded to an Excel spreadsheet. Lots of different things can be logged with a hobo data logger. There are books available to help us. There's a guide to energy management or handbook of energy audits that will give us ways that we can benchmark our building. You gather the information, chart it, and trend it, you can determine what's going on. We also have some organizations that are there to help us. ASHRAE, the American Society of Heat and Refrigerating and Air Conditioning Engineers, ACCA, Air Conditioning Contractors of America, AEE, Association of Energy Engineers, AFE, the Association of Facility Engineers, the IEP, the Institute of Energy Professionals. Onset does excellent webinars for hobo data loggers. RSCS is Refrigeration Service Engineers Society. The Fluke Meters does excellent webinars on Fluke test equipment. They can provide us guidance on energy management techniques. So in the techniques, we should be looking at preventive maintenance, minimizing ventilation air, building management systems, commissioning and recommissioning, other opportunities for savings, free cooling, premium efficiency motors. Assuming that equipment is properly installed and is operational, it will not get more efficient after the commissioned startup. Maintaining the equipment is the best way of assuring its continued efficient operation. Scheduled maintenance should follow the manufacturer's recommendations. So what should our maintenance be? We should do filter maintenance, wash evaporator coils, check our motors, belts, and drives, condensate drains, clean condenser coils, line insulation, electrical service, and refrigerant pressures and leaks, superheat, subcooling, delta T of supply air, ductwork, and duct insulation, and controls. Setting up the PM schedule should follow your O&M manuals. Scheduling should also take into consideration the environment. Having spent a lot of time in the textiles, you have dust everywhere, and that increases the frequency that some of your maintenance needs to be performed. Filter maintenance, how dirty is the air? Filters that are allowed to stay in too long will cause the evaporator coil to get dirty or even impacted, causing airflow restrictions and freezing coils. This causes excessive runtime. The outside environment will dirty up the condenser coil, and running dirty long enough will cause the coils to become impacted. No way to reject the heat, causing compressor failures. Again, added cost and added utilities. The next slide shows a chart put out by Carrier, and it represents the energy savings from washing condenser coils. It compares moderately clean coils to clean coils. It shows the measurement of the energy consumption in kWh and using 9 cents per kWh. It shows savings of greater than 30% savings just if you clean your coils. There's a lot of variables in coil washing. Time of the year affects it. Too early in the pollen season, you'll have clean coils, and then they'll be recoated as our pollen season shifts. grass cutters always seem to blow grass up into the condenser coils. The ability to get clean air from around the facility. I've seen facilities that installed their equipment too close to the building and were not able to get enough clean air around the condensing unit, and therefore they weren't able to make cold water. How do you control the system or systems? Per ASHRAE, only approximately 14% of the buildings have building automation systems. The building control system reduces energy costs by integrating the HVAC system with other systems so that all the systems can run at the top efficiency. So common opportunities with building control systems is lack of reset strategies for discharge air temperature and duct static pressures in air handlers, chilled and hot water temperature resets, differential pressure resets on chilled and hot water distribution loops, lack of use, occupancy sensors for common areas aren't used, faulty sensors or sensors in wrong locations, or night setbacks aren't used. We all like to walk out and forget to turn systems back. Improper setting, heating and cooling set points, outdoor air during morning warm up, dead bands are too far apart or too close, improper schedules for air handlers and fans and exhaust fan operation. The biggest reason why building suffers is inexperienced workforce. Many people don't know how the controls work or even when they work, and this will only continue to get worse as we continue to have less and less people entering into the maintenance field. Building analytics is a great building management tool that will combat inexperienced help. Based on the available information, many buildings consume up to 30% excess energy beyond the original design expectation. Benchmarking of the building data allows us to predict and monitor whether systems are in the peak range efficiency. They provide for automated fault detection and diagnostics by providing live data for comparison. They help alleviate potential problems by integrating advanced energy systems that they can look at and analyze whether things are working properly. The goal of commissioning and recommissioning is to ensure that systems are meeting design performance requirements, and if not, identifying correct why. Equipment and system sizing is based on calculated heating and cooling loads. Is the space being used for the design purpose? Was this facility bought and at one point in time it manufactured textiles and now it's being used for another type of product? So what are we using the building for? Every installation is different and not a one size fits all. So you take the opportunity with recommissioning to make sure that the equipment is performing at its top efficiency. Recommissioning a building's HVAC system is a basic and relatively inexpensive task that often has less than a 1-year payback. Basically, engineers make sure all equipment is at the right settings, that controls work properly, and that other equipment functions are designed as designed. Measure and verify airflows and chill water flows to make sure they're at design. I stumbled on this quote a number of years back, and there's a tendency to seek funding for energy saving projects first because they have an associated payback that can be used to justify the expenditure. However, that can be a false sense of savings because one can't know the true cost of operating the building if the current system fails to perform effectively. Before throwing money at new chillers, we need to take steps to understand precisely what is going on with our current system and how we're failing to meet our goals. More thorough evaluation using measurable parameters can lead to smarter solutions through wiser spending or sometimes simply through better practices. As businesses try to get back to normal in the wake of COVID-19, should look at to pair efficiency upgrades with healthy building projects. Anytime a building is starting to consider capital improvements to their system, the door is open to look at how can they improve their energy efficiency. Other opportunities is minimizing ventilation air. One of the things that has come about with the COVID-19 is we've opened ventilation up to get as much outside air in a building as possible. By doing that, you're now heating this in the summertime. You're heating or trying to cool air that is too hot, and in the wintertime, you're trying to heat air that is too cold. So, good working on indoor or minimizing your ventilation air is very important right now. In heating and cooling load calculations, the introduction of outside air is usually a large thermal load. Controlling the outdoor air to the minimum required for safe working environment will save energy. ASHRAE 62.1 is our ventilation acceptable indoor air quality guide. The ACCA Manual N is used for HVAC load calculations with Table 14 giving ventilation requirements. Good ventilation means having enough ventilation, but not too much. Too much ventilation doesn't help at all in terms of getting buildings drafty. Sometimes it's as simple as stuck air intake or exhaust vents or repairing broken dampers can cause both ventilation problems and waste energy. Are my outside air dampers controlled by CO2 sensors? Getting everything back in shape improves the air quality and comfort while saving money. There are times of the year when a system can use outdoor conditions to cool the building or process using the standard cooling components to distribute its cooling effect. This is done with air side economizers, with enthalpy controls, and with plate and frame heat exchangers. Premium efficiency motors is another area. The difference in operating cost between a 92% and a 93% efficient 20 horsepower motor can be between $50 to $120 annually. The variable speed motors is another area that we can look at. Rewinding failed motors is not cost effective in high use applications. Studies have shown efficiency loss of 2 to 3% every time you rewind a motor. VFDs can be used for fans and cooling tower fans and pumps and require appropriate setback conditions. They're used to match the building and the load to what you're supplying. Programmable thermostats with proper programming, nighttime setbacks, improved belt systems and belt drive systems, chiller maintenance, brushing the tubes on the chiller, chill water and condenser water resets, chiller sequencing, and then if you don't need it, turn it off. That's one of the best ways to employ. So while preparing to succeed in energy management, you got to look for all opportunities. You got to seize the opportunity, examine the ABCs, manage your time like you do your money. Look for opportunities. There's low-hanging fruit. Look for opportunities and keep looking. As you identify one, another one will present itself. Talk to others, network, attend functions like today, partner up, and let all your resources work for you. Do not try to do everything yourself. Involve others. Create an energy team. Keep your facilities efficient for life by relying on proven equipment and methods. Measure it to manage it. Document your savings, cost avoidance, productivity increases, and other things. The important thing is to get started. Enjoy yourself and have fun. Don't forget to educate your boss along the way of the positive contributions that you have made. Improving energy efficiency may be the most profitable thing that we can do in the short term. How much we will actually benefit from this opportunity depends on how we approach it. There are no real gold nuggets in any of our presentations except to get started. A quote I read about a competent energy manager does not wait passively for proposals. They aggressively seek every opportunity within the facility for lower energy cost and relentlessly educate themselves about every method of lowering the energy costs that could apply to their facility. And with that, I'm through.
Thanks, Kevin. That was a lot of technical information for me personally. But I'd like to echo what Mike said previously about increasing efficiency as a process, and that's how I kind of view sustainability in general. Is that it's an ongoing process. It's a path, not a destination. It's the journey. So while you were talking about preventative maintenance, I was thinking about things around my own house. If you just start with cleaning things, cleaning your changing your air filters or cleaning coils on equipment, replacing parts that aren't running efficiently anymore, or just updating your technology in general. It's all a process, and you can start small and then work your way up. It's not something that you have to do everything all together. It's step by step. So had some really good takeaways from your information. That was great. Thank you very much.
Thank you.
All right, so with that, we will turn it over to Sam, and I'm excited to see what this is all about behind him. So, Sam,
All right.
Leave it up to you.
Yeah. Get everything shared here. All right, can you guys see that okay?
Yeah,
Yep.
looks good.
Excellent. Great. So I'm going to echo a little bit about some of the things that both Mike and Kevin talked about. Gary, you and Mike were talking about, the importance of keeping those doors shut. So we're not only going to close the doors here, we're going to look at what else we can close to make sure that we're not paying to heat and cool the outdoors. So when we talk about the building enclosure itself, it's important to think of that building enclosure as a part of that HVAC system because they go hand in hand. It's good to look at the whole building as a system. One question that I ask a lot of my students is, what's the largest duct in your HVAC system? And we get answers like, oh, it's the return or it's the trunk line. But no, it's the building enclosure. That is the container that is holding all of the air that we are paying to condition to a certain temperature. And so just like we don't want to carry water around in a bucket that has holes in it, we don't want to condition a building that has a bunch of holes in it either. It's a similar principle. So what you see here in this photo, all these fans lined up in these doorways, this is what's called a blower door system. And this is what we measure air tightness in a building with. So we're able to bring that building under a certain positive or negative pressure. We can test either way. Sometimes we do both and take an average. And then these things here that you see on the red cases are manometers. And so if we know pressure at the fan and we know the building pressure, we can calculate the flow through the leaks of that building at that given pressure. And so I'll get into this a little bit later, but I just wanted to introduce what this is. And that's how we measure that, to be able to benchmark to see maybe how tight or leaky that building is. Because if we're having problems maintaining temperature in a building, the blame usually immediately goes to the HVAC. But again, there's another side to that. It may not be the HVAC system's fault. It may be the building that the HVAC system is trying to serve. So going into that, some benefits of having an airtight building enclosure: energy efficiency, of course. We're not trying to heat and cool the outdoors. Kevin talked about this load calculation that you have to do. And this is what a mechanical engineer or mechanical contractor would do to determine how much HVAC that you need for your building. And part of that load calculation is infiltration through the building envelope. And about 9 times out of 10, this is a guess. And one takeaway that I really like from Kevin's presentation that I'm going to remember is, if you're not measuring, you're not managing. So if we're not measuring that building airtightness, then we really don't know what it is. And in many cases, we've seen load calculations be off by, maybe even 50% just due to infiltration alone. And this can go in either direction. If we're underserving it, then yeah, we're during the summer months, as we generate heat off of our machines that are in the manufacturing plant, plus the hot weather outside, if it's being underserved, a lot of the blame there just could go to the building envelope, just because of leakage, because it was just underestimated. Same in the other direction, it may be tighter than they thought it was, and then if you're overserving that, then you can get some humidity issues there. Humidity has a direct relationship with all of this too. Where does a lot of that humidity come from in our summer months? It comes from the outside. So if we have a tighter building envelope, we have better control of that humidity indoors. And that goes into the indoor air quality aspect here. Humidity plays a large role in that, as well as the off-gassing of maybe some of the other building materials that we have too. If we have a tighter building envelope and good ventilation, then we have better control of that indoor air quality. Water as well, whether it's bulk water, humidity, ice dams and roofs. When we don't really have that much of a problem with ice dams in North Carolina, but in other climates we definitely do. And then pollution coming in from the outdoors, especially if you're in an urban environment. And of course, fire and smoke control. Air is fuel for fire, so if we have a tighter building envelope, then we can, a lot of times create less draft, and sometimes that fire will spread slower than it would otherwise. So there's a lot of benefits to, other than energy efficiency, to having an airtight building. Sometimes comfort is one of them. If you have an uncomfortable working area, you can help mitigate that by tightening that building enclosure to make it match your mechanical system a lot better. And then at the same time, you're saving energy as a nice benefit. So I want to introduce this credential, building envelope commissioner. So this is a person that you would hire if you're doing a retrofit to a manufacturing facility, or if you're building a new plant. This BC, you see this BECX here. This is the building envelope commissioner. This is the person that you would work with from beginning to end, from selecting the correct building materials, how they would be installed, and then testing everything out along the way to make sure that the reality of the building, the finished product, is matching the initial design, so that everything is going to work correctly. So it's always nice to work with a person like that if you're trying to improve your energy efficiency or whatever it is that you're trying to fix through tightening the building envelope. And so it's important to mention the air barrier. Every building has one. Some are much better than others. A lot of people will get insulation and air sealing. Maybe they think they're one and the same, but they're really not. There's materials that do both, but they're two different things. If you just have insulation along your walls, air can still leak in and through that. I mean, especially if the material is like fiberglass or cellulose or something like that. But the air barrier itself, it could be a number of materials. It could be the type of sheathing you have on the outside of the building, whatever material you like to use, if it's a fluid applied membrane, you have to have that in order to keep that outdoor air from coming in and that indoor conditioned air from going out. It's that definitive point in the building enclosure that defines inside from outside. And so if it's riddled with holes, then you're going to have a very poor performing building there. And usually the air barrier will be alongside the insulation. You usually want to have those two things together, whether if it's two different products that are aligned or one product doing both. So a question we get a lot is, where do these leaks most commonly occur? It really depends on the building. In manufacturing facilities, you could have, there's all types of building types out there where manufacturing occurs, but a lot of people think windows and doors. And that's usually at the bottom of the list. A lot of the times our most, the sealing the holes for the most bang for your buck occur usually along the ceiling, at the roof, along the top. But essentially, this air leaks are going to happen where two materials meet that are not deliberately sealed. And then any holes that we have going through what would be our air barrier for whether if it's plumbing, mechanical, or electrical. If you can see here in this photo, this is a massive hole here that was cut through these pipes and then not sealed back over. Really, if you're going to run pipe, you should use a hole saw and then seal around it. You don't have to cut out a great big rectangle like this to run a small circular pipe. But we see a lot of this stuff in all types of commercial buildings. And then we see materials that just aren't applied correctly. Building materials are just like anything else. They come with an installation manual. And if you don't read and follow the manual, things are going to happen. So here, this flashing tape was affixed to a material that it wasn't designed to be attached to. So then it peeled back off, and so it's not going to create a good seal. So from anything from just the design, poor installation, these types of leaks can occur for a number of reasons. And the HVAC ductwork is an important one to mention too, especially if you have returns or supplies or systems located on the outside of the building envelope, whether if they're on the roof or along the outside, or along the side of the building somehow. If that ductwork is leaky, then you're just sucking in outdoor air into the building, or removing that indoor conditioned air to the outside instead of running it back through the return. So that plays a large role in this as well. Yeah, again, more common air barrier deficiencies, again, just material compatibility, things that we see, people trying to use certain materials that don't work. We see quite a bit of that in existing buildings. So who regulates this stuff? Well, here in North Carolina, we just adopted air tightness in our commercial building code last year. Buildings don't have to be tested. Building material manufacturer specs are allowed, but a lot of times, if you add all that together, it doesn't always add up to be a good system overall. The best way to do it is to test it, the end product, to make sure that it is going to perform. The way that we measure air tightness with a blower door, we look at that flow at cubic feet per square foot. So cubic feet of flow per square foot. So cubic feet per minute. And that's per square foot of envelope area. So all the walls, roof, and the floor. And in North Carolina, what we expect, if you're going to test it, if you're going to take that route, that's going to be 0.40 CFM per square foot of envelope area, which is, not a difficult target to hit. The Army Corps of Engineers has their own air tightness standard, and theirs is 0.25, which is a very nice building envelope. That's pretty tight and not unreasonable to hit for new construction either way. So that's how we benchmark air tightness, and that's how we look at it. That's the number we look at per square foot of envelope area. So this is a study that was done, and forgive me, this chart is in cubic meters and not CFM, but we've mapped out here what this means. And so we see these blue dots, from 1955 to 2005, and these are different buildings. Each one represents a sample taken. here at this bottom line, this 0.25, this is that Army Corps of Engineers standard. We see some hit here. And these are buildings that had a building envelope commissioner working with them to make sure that everything was going properly. 1.8 CFM per square foot. We see here this second red line coming up. That's a pretty leaky building. That's leaky enough to where it's going to be, difficult to control humidity and temperature. Some parts of the building might be comfortable, some may not be. Definitely not very energy efficient. And then we see all these other ones that are up here. In some of the mid 90s here, we see some of these way on up here. We're basically living outdoors when we see buildings that are this leaky. So this is what I was going back to earlier, is you really don't know what you have unless you test it. And so if you're having some energy efficiency issues that you might think be HVAC related, it's likely going to be worth your while to take a look at that building envelope to see if it's the building itself that might be causing it and not the HVAC, because they do go hand in hand. So when we look at our air barrier, when we try to define what that is, it's nice to have a sectional drawing of the building. And when you take that air barrier, you want to be able to take a pencil and then draw all the way around that air barrier of the building and not lift the pencil up until you get back to where you started. And so that's what this red line is that we see here. And sometimes we have rooms in our manufacturing facilities that may not be a part of the conditioned area. So we don't want to include that, whether if it's a supply room or a basement or something like that, or a storage room that's not conditioned. So it's important to differentiate those from the rest of the building to see exactly where that definitive line is, but that defines inside from outside. So drawing that out to really wrap your head around to see what actually is your building enclosure helps a lot here when you go around and look at your building. And then all the points where it can leak. Whenever you see a corner, yeah, you've got two materials that are meeting. Are they sealed? Is there a hole there? Where do you have pipes going through? Is there going to be a leak there? So a lot of the times where we find problems are, where we have these circles here. So where there's going to be a turn in the materials, where we have any kind of penetrations, that's usually going to be the culprit. Here. Oh, let's go back. And so this is just another diagram here to show, if your building has an elevator in it, a lot of the times that elevator penthouse is going to be connected to the outdoors, and there can be ways to seal that. So just, having a good understanding of where that is really helps, and where those penetrations are can help you track down where some of these problems might be. And, as we're running our blower door system that I showed you at the beginning, what we're doing essentially is during that test, we are exaggerating all of the leaky points in that building to measure it. And as we're doing so, if we're able to walk around that building with a thermal camera, we can really see where those problem areas are, especially if we have a good temperature difference between inside and outside. So during the winter months and the summer months are the best time to do that. You can test anytime, but to really get good, nice photos of where the problems might be with a thermal camera or during those peak seasons for winter and summer. Hot air rises. So I'm going to talk a little bit about this later, but heat moves in all directions. So if you walk around with that thermal camera, you may not only see air leakage, but you may also see some areas where some insulation might be missing or maybe not properly installed, and other things such as that, maybe some moisture issues. So this is a photo that we took a while back. This is an elevator at the top floor. This is what I was talking about earlier. So as we are running our fans to depressurize the building, we can see this cold winter air being pulled in. That's what the blue stuff is on this elevator shaft. So we're able to identify that, the right above this elevator here is an area that we would want to seal to make this building tighter. And then we can see some air leaking up under this wall here. But, walls are kind of a tough thing. If they're covered with drywall or plaster or something like that, or brick, it's going to be tough to to access that. But a lot of our low-hanging fruit is going to be up in the ceiling and areas that we can get to. Some more thermal imaging here. As we're running the fans, we can pull that in and get a nice shot of it to see where these problems are occurring. Fog is another way we can do this. If you ever do this on your building, call the fire department and let them know, because someone will call and think your building is on fire. We've had that happen before. But you can take theatrical fog machines and take these blower door fans as you're running the tests. If you're pressurizing the building, you can put some fog along the roof line and then step outside and see where that fog is escaping from to see where some of your air leaks might be occurring. You can also find some roof leaks, the source of some roof leaks this way as well. We've also done that. So the tricky thing about air is it's invisible. So any way that we can make that air visible is going to be a nice, easy way for us to track down where those problems are occurring to fix things up. So we have 3 pressure drivers that cause a leak in a building. The 2 most common ones are wind. Yep, the wind's blowing. And if we have holes in our building, then we can get outside air moving in. Fans, our mechanical systems, they induce pressures on the building, ventilation, things like that. So as we have air come in, that air's got to go back out someplace, and it usually just goes back out, leaks in the building. But stack effect is another one that plays a really big role here, especially in manufacturing buildings. In the winter, what happens is that hot air rises and escapes out the top, and at the same rate, it pulls in cold air from the bottom. So if we have maybe 10 pascals of air, of pressure at the top, we could have, or negative 10 here at the top, we could have positive 10 coming in. So it's going to be equal on both ends usually. That's one way that we can kind of help differentiate that. If we have a lower pressure at the top and a higher pressure at the bottom, then that means that more of our leakage is at the top than the bottom. But that's something that your building envelope commissioner would likely do if you're looking for leaks, if you ever decided to get your building tested. But even if you don't have any fans running, you're going to have equipment running for manufacturing. It's going to create heat. In the summertime, this is reversed. So that cold air is going to fall out. The air that you're conditioning with your HVAC system is going to fall out the bottom and then pull warm air in at the top. And that's just going to make it warmer inside. And so if you're able to tighten that building up to reduce that stack effect, it's going to allow that HVAC system to satisfy the thermostat a lot easier and not have to work as hard. So along with the wind that occurs, that creates leaks in buildings, and the fans that we already have running, the stack effect is always working against us too in the more extreme times of the year. So the taller the building is and the larger difference we have between indoors and outdoors as far as temperature goes, the stronger that stack effect is going to be. But we can mitigate that by sealing up the building as much as we can to stop that from happening. And I'm not sure who took this photo, but it's pretty famous. If you just Google building stack effect, it's one of the top results. But they had this building covered to do some work, and you can actually see this until it's in the wintertime. This is where that line is that changes from a positive pressure to a negative at the top. And so you can see that air ballooning upward and getting sucked in here towards the bottom. So so you can tell there that was taken during the winter, where it was warmer inside and cooler outside. And like I mentioned, the taller the building, the stack effect gets that term from working like a smokestack or a chimney. The taller it is, the stronger it's going to be. The leakier it is, the stronger it's going to be. And so if you have a parking deck or something like that underneath, then you can be bringing in other things along with that air that you may not want to be breathing indoors. We don't really smoke inside anymore. It might be time to update that, but you can kind of see where this diagram is going. But I mentioned before, it's not just energy efficiency that we're always focusing on. Sometimes it can just be a nice benefit if you want to focus on something else. For example, in this building was very leaky in between floors. And so it was condensing. during the summer, warm, humid air was coming in between floors, condensing on cold HVAC, and then dripping on this wood, allowing it to grow mold and then rot. So sometimes a leaky building in a humid climate can also cause some structural issues to reduce the structural integrity of the building itself. So as we can use air tightness testing and air tightness improvements to fix this kind of thing, and then at the same time we get a lower utility bill. So if you're ever wanting to look into getting a test done, I talked about the air barrier and planning that out. The time of day is nice, especially if it's a current plant that's under operation. A lot of the times they'll come in and do the test at night after everybody has gone home for the day. Sometimes you can get nicer thermal images at night as well. The less people that are in there running around, the easier the test will go. And then just having everybody involved, from the building owner. If you have a building engineer, it helps to have that person there. HVAC contractor, just to kind of see the building automation software. Somebody who's knowledgeable to run that, to make sure the mechanicals are off when the test is run and all that. So just some things to look out for. One question is, well, how many fans will it take to test my building? We have a calculator for that on our website. You can just input some information about the building, and then it can predict the amount of fans that it might take to run that kind of test there. And so to calculate that number I mentioned earlier, we look at air leakage in buildings like this at CFM per square foot of envelope area. So we would have to figure that up. How much floor area do I have? How much wall area do I have? And again, how much ceiling area do I have? And we add all those up. And that's the number that we would need to go by. And there's a little bit of prep work involved too if you're going to have one of these tests. Sealing up exhaust fans, any leakage that we don't want to count. Depending on how big the building is, depends on how complex the test is going to be. We want all interior doors opened up and all mechanical fans turned off and things like that. So that's why a lot of these tests happen at night for manufacturing facilities. And as we get the test set up, that's what it looks like. The number of fans, again, just depends on the building. And you run the fans with software on a PC, and you have all the digital manometers connected together that are talking to the software. So the laptop knows what each fan is doing, and then you have some tubing that references the outside. Again, this is a manometer that we're using, so it's just measuring pressure in one space versus another. So we have to have a reference place, which here is outdoors. And then we want to see what the pressure is doing to make sure that we're reaching that target pressure throughout the building. So we have other tubing. If we have multiple floors, we want to see, make sure that the entire building is getting under that pressure target. So as we're running the test, in this case, we are depressurizing it. And so we have a little fog machine here, and the roof here is supposed to be our air barrier, and we can see that it's leaking quite a bit. Pulling a lot of air into that roof deck. So this was a new building that was built. So there's some spots back up there that would need to go back and be fixed. But some additional air tightness issues, air tightness, if we look at top 10 warranty callbacks for new building construction or a major retrofit, one of the biggest things that all of these have in common is water. So, Kevin mentioned moisture issues, and a lot of these water issues have to do with moisture coming in through the air. And so if we can stop that, then we don't have a lot of these problems that I mentioned here, squeaking floors, condensation, things like that. So some of the more expensive problems that are going to occur because of air leakage are probably going to be the primary things you're going to focus on if you're having those kinds of problems. But as you go and fix those, you're going to reduce your energy bills because a tighter building is going to be more efficient, so that the mechanicals don't have to work as hard. And again, talking about moisture, this is from Building Science Corp. But if we're looking at 1 week, in a mixed humid or a hot humid climate, kind of like we have in the summertime, if we just have one 4x8 sheet of gypsum board with 1 square inch hole, you're going to have vapor drive go through just from diffusion through the material. But if you add that 1 inch hole, you can see how much more water will drive through that board in 1 week. So moisture issues and air leakage go hand in hand. And here you can see why. But you don't have to always test the whole building. If you know it's a window issue or something like that, you can test the window independently with a smaller system. You can test the roof alone if you want to. Again, this is a fog machine that's hooked up to this, so you can inject fog and then pressurize the building and then see where that fog is going to escape. So there's all types of ways we can investigate a building enclosure, depending on what we want to focus on. But we have materials on our website. I'm from a company called Retrotech. We manufacture all types of air tightness materials, and we teach building science to construction trades, HVAC contractors, builders all over the world. So we have all types of content there on our website and as well as on our YouTube channel. So if you're curious about this and want to dive into it a little bit more, you're welcome to. And while I still have just a couple of minutes left here, one thing that I'll show you is just what some of this looks like. If we're running fans, this was in an actual building in New York City where we used about 33 of these fans. They were having energy problems and really couldn't afford the utility bills out of their budget. And so we went and tested it. And so we can see using that fog machine, we can see where a lot of these leaks were occurring. At the top of the building, there were all of these louvers that were up there in the elevator penthouse that were rusted open and didn't have seals, and we could see that smoke escaping through there. And if I fast forward a little bit here, you can see we're using a thermal camera here. So this is at the top floor in a stairwell. We're depressurizing the building, so we're bringing cold outdoor air in. And we can see this corrugated metal here sitting on top of the concrete wall. Someone attempted to stuff some fiberglass insulation in here, but that's not how you air seal a building. So we can see that cold outdoor air getting pulled in, and that's going to be a large part of that problem there too. So I just wanted to have something in here just to kind of show you what this looks like in the real world. And that is what I have. I appreciate ECU having me here today.
Thanks, Sam. That was awesome. Really awesome. When you were talking about the elevator shaft and you were showing that image, you mentioned about interior finishes. You can't rip that stuff apart if there's an air leak. So these tests can be run before interior finishes are put into a building during the construction phase, correct? Or
yeah, absolutely. I mean, if it's a newer build, you can definitely test because your air barrier material is going to be on the outside of that. And so, yeah, that's usually going to be the best time to test if you really want to investigate to see what's going on before you close everything up. But if it's already an existing building that's been established for a while, it's pricey to go in and tear that stuff out just to seal an air leak. If you can just find where the bulk of it is. Again, like I said, usually it's going to be along the ceiling or the floor. It just depends on how that building is constructed.
That's awesome. That's really great information. So with that, I'm going to thank the speakers for joining us today. We appreciate your time very, very much. And then I'm going to go ahead and open it up for discussion. Any questions? Nobody has sent me any questions through the chat, but I'd like to open it up. If you'd like to unmute yourself and ask any of our speakers any questions, you can do that now. Okay. Nobody wants to ask a question? I had tons of questions. Okay, well, everybody included their contact information, so if you do think of a question or if you'd like to contact any of us at ECU through the center or any of our speakers today, you have all of our contact information. Again, all these presentations are available to you. If you are joining us through the meeting link and you did not register, I may need to get your contact information through the meeting just so I can keep in contact with you. Otherwise, I would just like to reiterate again that we are, the center does run on sponsorship and donations. The EPA grant funding that we receive is for our research, and donations and sponsorships help us with community and student engagement. So if you'd like to make any kind of donation to us, small or large, that would be very much appreciated. It's hyperlinked here to the donation site. You'll find that again in the presentations today. Otherwise, I'd just like to thank everybody again for joining us today.
There's one question in the chat.
There is a question in the chat. Thank you for pointing that out. Where to find more on compressed air efficiency improvement? And Mike just popped in there. DOE Compressed Air Challenge.
Yeah, that's one of the best sources. There's all kinds of information, but if you just go to a browser and type in DOE Compressed Air Challenge, there's all kinds of stuff. They have a probably over 100-page booklet on how to optimize an air system from the demand side and the supply side, and it's really, really good. And they have training courses available for the DOE Compressed Air Challenge, and we sponsor those occasionally. But that's a really good source. And just if you just put in type DOE Compressed Air Challenge in a browser, you get some really, really good stuff for compressed air energy efficiency ideas and tips and topics.
Thanks, Mike, for jumping in there.
Sure.
Usually the chat dings at me to let me know that there's somebody there, so I do apologize. I almost missed that. Otherwise, any other questions from anybody that's still with us? We maintained a connection through this whole event, which I'm happy because we've got some real severe weather going on right now, so happy to see that. Last call for questions. Okay. All right, well, we look forward to our next event on July 29th on pollution prevention and how we can make that pay for North Carolina industries. We will have some information coming out soon about that, and hopefully we'll have the registration process down pat by then, so it shouldn't be so complicated to get everybody registered for that. Otherwise, again, thank you so much to Sam, Kevin, and Mike for joining us today and giving us your time, and I hope everybody has a good, safe rest of your day.
Thank you. Appreciate the opportunity.
Thanks again for having us.
Yeah, thanks.
Yep, thanks.
Take care, everybody.
Bye.
See ya.
Bye.
Thank you. Bye-bye.